Okay. Welcome everyone. This is our two last meetings of Coronactivity 2, so let's enjoy it. Okay. Today is here with us Björn-Martin Sinnhuber. He's senior scientist at the Institute of Meteorology and Climate Research at the Karlsruhe Institute of Technology, graduating in physics at the University of Bremen, Germany. Björn spent a couple of years in the United Kingdom before joining KIT in 2010. His current work involves climate modeling, aircraft observations, and the planning of the future satellite missions. Björn-Martin teaches atmospheric physics at the KIT and the University of Bremen. So let's listen to him. Björn?
Here's my audio. Oh, sorry. So thanks very much for inviting me here. And yes, I want to present you some impressions and results from the SouthTRAC aircraft campaign that we performed about a year ago in Tierra del Fuego and in southern Argentina and Chile. And what you see here is our aircraft, the HALO, the German high altitude and long range research aircraft, parking in front of our hangar, or the hangar that the Armada gave us for this purpose here in Rio Grande. But why did we all do that? I mean, okay, let me see. Okay, yes. So we all know that climate change is a reality. And for example, here from the IPCC fifth assessment report, we see that surface temperature, the global average, have increased over the past 150 years or so by about 1 degree, with already large consequences. But if we look into the future, we see climate model projections here in blue, the more very optimistic scenarios, where under these optimistic scenarios where we need to act very soon, I mean, actually we need to get the turnaround basically now, temperatures can be stabilized at about 1 more degree or so temperature increase, whereas the more pessimistic and maybe it's the more realistic scenario, temperatures will increase by the end of this century by about 4 degrees or so globally. But what is really of importance for all of us, for society, is the regional manifestation of this global climate change. I mean, what does it mean in terms of temperatures, precipitation, droughts, extreme events, and so on regionally? And when we talk about this, we need to look also at the natural modes of climate variability, again taken from the IPCC report. In the northern hemisphere, in Europe, for example, the natural climate variability is very much dominated by the North Atlantic oscillations, the NIO here, that we see here with corresponding temperature patterns and precipitation anomalies that are centered around the North Atlantic and in Europe, North Africa. Whereas, as you certainly know, in South America, in the Pacific region, the El Niño Southern Oscillation is really a large mode of variability, of internal climate variability, that controls precipitation and many regional climate effects there. And if we go further to the south, then the southern annular modes, the SAM, become important modes of internal variability that control temperature changes and precipitation and related effects there. And we already know for quite a while, 20 years or so, it became clearer and clearer that the Antarctic ozone hole, so this depletion of the protective ozone layer, is not only important for shielding us against harmful UV radiation, but the ozone hole also projects on this southern annular mode of regional climate variability in the southern hemisphere. And what's shown here on the left are model simulation, climate model simulation, and on the right-hand side, observations that show that the ozone hole had an important effect on pressure systems, that's on the top row here, and on surface temperature, that's the colors here, and winds, that are the arrows here, on the southern hemisphere. So in particular, the Antarctic, large warming of the Antarctic Peninsula, and here, down here on the right side, it's the tip of South America, warming of the tip of South America due to the Antarctic ozone hole. Now, the Antarctic ozone hole, due to our all effects of banning the ozone depleting substances, is already healing, and we expect a full recovery sometime in the middle of this century. Now, what I'm showing here on the right-hand side are climate model simulations that our colleague and good friend Rafael Fernandez from the University of Cuyo in Mendoza in Argentina has performed, doing 2 sets of climate model simulations in black and in blue as a function of time here. So the ozone hole opened up at around 1980 and will be gone sometime in the middle of the century. And in red are some observations of the ozone mass deficit in million tons of ozone. It peaked at around 2000. We are now at 2020, already a good deal towards the recovery. It's healing, but there is a large uncertainty in these climate model simulations, depending on the scenarios, in particular of natural substances from the ocean that contribute, and so on. And that's something that we further investigate during this aircraft campaign, and already got some very useful results that help us to better constrain these models. Now, coming to a very hot topic, that is the large wildfires that were occurring at the same time at the end of last year in Australia, and to some extent this year again. And at about this time here, November 2019, this paper has been published showing that there is a connection between the stratospheric polar vortex, so that's intimately connected to the Antarctic ozone hole, and extremes of hot temperatures and extreme dryness, so reduced rainfall over Australia, that are related to what's going on at around the ozone hole. And that was to a large extent responsible for these very anomalous wildfires here and this strong biomass burning. In order to understand why this is so, we need to look up higher in the atmosphere. And that's shown here schematically, a scheme here drawn from the tropics to the South Pole and from the surface to essentially outer space. So we have the different layers of the atmosphere, the troposphere here, the stratosphere, the mesosphere, and then the thermosphere above. The ozone hole sits about here. And we see all the processes involved, the biomass burning that brings pollutants here, also volcanic eruptions. And quite important is this wave-driven circulation. So that's a large-scale circulation that brings air from the low latitudes to the high latitudes and down here at the high latitudes. And that influences the weather systems here, the southern annular mode. And this circulation is driven by atmospheric waves, so-called planetary waves and gravity waves. And this is something that in current climate models is still not very adequately represented. So what, and I'm talking a little bit more about that in a few minutes. So our goal was to go here to the southern hemisphere and investigate in particular these processes in this area here. So from the ozone hole and pollutant inputs and these waves here, the southern hemisphere, because that is not well captured by observations so far, in particular in the upper troposphere, lower stratosphere region. So we formed this project, this campaign, SouthTRAC, standing for Transport and Composition in the Southern Hemisphere, upper troposphere and lower stratosphere, in order to better understand this. And of course, that took some time, to building up a team of groups, involved here are different groups from German research centers and universities, but also colleagues from research centers and universities in Argentina and Chile. And for example, we had a first science workshop 2 years ago, a bit more than 2 years ago, October 2018, in Buenos Aires, where a lot of these colleagues came together, defining the campaign. Half a year later, we had a similar workshop in Santiago de Chile to preparing all this. And then finally, last spring, about a bit more than a year ago, we finally went to the tip of South America, to Terra del Fuego. Very nice landscapes there. And in particular, we brought along our research aircraft, the Halo aircraft, here standing in front of the hangar on the first day when it arrived. And you see this is a converted business jet, a Gulfstream business jet, full with measurement equipment. It has a nose boom here to measure temperature and winds. Has a lot of inlets here, trace gas inlets on the top of the fuselage to pump in air that will be then analyzed for its chemical composition and other aspects inside, with instruments inside the cabin. And in particular, we have below the fuselage a remote sensing instrument. It's like an infrared camera. It's a so-called Gloria instrument that was developed together with our colleagues, Research Center Jülich, that observes like it's nicer to see here in this close-up. So it's like an infrared camera with a very high spectral resolution that gives picture of the atmosphere, where we then get information on a lot of trace gases and fine scale structures like these gravity waves. And I'll show you examples of that in a moment. So that's a picture of how it looks inside the aircraft. We typically have 5 scientists on board and 3 crew members, so 2 pilots and 1 technician. And this aircraft can fly for about 10 hours. So that gives us quite a long range. And we used that here. We had quite a lot of, we came, of course, from Germany here to Rio Grande, and then, and we're also to Punta Arenas in Chile, and had a lot of flights here down to the Antarctic and over South America in the time frame between early September 2019 and middle of November 2019. So what did we find? Some highlights here, and of course this presentation is short. I cannot show all of these, but one highlight is, or I don't know if it's a highlight, maybe it's a low light. We found lots of pollutants from biomass burning here, primarily from the Amazonian region here, but also not shown here, but on other flights, we clearly could trace that down to pollutants that came from the Australian wildfires here. In this case, what's shown here is peroxyacetyl nitrate. It's a pollutant that produces ozone in the upper troposphere, and is here, the strong enhancement here in yellow and red are clearly coming from the Amazonian region. Earlier on, I was talking about these waves that are very important of driving the atmospheric circulation and that are not well represented in climate models. And these waves are moving air up and down in the atmosphere, and during the upward motion, the air is cooling, and if it cools below a certain temperature in higher up in the atmosphere, clouds can form. In this case, polar stratospheric clouds that are very high up in the atmosphere, much higher than ordinary clouds at about 20 kilometers. And because they are so high up, they can still be illuminated by the sun from below when the sun is already below the horizon. And that's what we observed just standing in front of the hangar in Rio Grande in September. We observed over the mountain ridge, the southern tip of the Andes, the westerly winds are, this is a global hotspot of these gravity waves, because there are these strong westerly winds that hit the Andes and can then excite waves that move upward, and we can see them as these very nicely looking gravity waves or polar stratospheric clouds that also play an important role in the chemistry of the atmosphere. And with the aircraft flying around these waves, we could observe them with the Gloria instrument, and this is an analysis that our colleagues at the Research Center Jülich did, and creating a tomographic 3D representation of these waves. And what is shown here in red and blue alternating are warmer and colder temperatures. So this, to the experts, this gives information about the wavelengths, its orientation, phase speed, and all these parameters that are important to better represent them in climate model. So this is a very nice result, and already is in this moment helping to improve the models. Now, we need to fly around this with an aircraft in order to get this 3D tomographic picture. That takes about an hour or two. So certainly we can't do that every day. So what we are doing right now, and Anna mentioned that just at the beginning, we have just proposed to put essentially this instrument onto a satellite as a new Earth explorer by the European Space Agency. And that would give us, this is the same situation as we would see that hypothetically from this satellite that we called KIT. We would get a picture from the mid-troposphere up to 100-kilometer altitude of this wave structure. And if that could be realized, essentially that would give us like the SouthTRAC campaign, but we could come back essentially every day to South America. So, this would be a very nice extension in a sense of what we had done in the campaign. So I think my time, to just give you a brief overview, is almost running out. So just give you another picture of how that looks like here. It looks almost like now coming to the Christmas season. And with that, I'm thanking you for the attention, and I'm happy to answer questions or go into a discussion. Thank you.
Okay, thank you. Thank you, Björn. And okay. Do you have any questions for him?
Yes, I have a question, Anna.
Okay.
The subject is extremely interesting. I think it's very concerned with the future. And I didn't understand the second slide. Can you go back, please?
Yeah, let me see. Oops.
Yeah, Martin.
Let me see if I can go. This one?
Yes. Here on the right, the zero, the zero on the vertical axis is the no warming respect the pre-industrial area, isn't it?
That's a good question. I was not entirely sure. I took this picture from the IPCC assessment, and I was also wondering, and I have to admit, I didn't check that very carefully. Here on the left-hand side, the zero you see here, we are going from in the late night. This is from observations on the left-hand side, and we are going from below zero to zero at about in the zero. So zero is basically this period here in the middle of the 20th century.
Yes,
but
yes.
it doesn't look as if this is the same scale here. So I'm not entirely sure. And of course, this is very important then, whether this would be 1 degree above current or 1 degree above pre-industrial. I think the zero here is not really pre-industrial, but it's middle of the 20th century, which is already higher. Like here, you see the mid of the 20th century is already a few tenths of a degree higher than the pre-industrial time. But we need to check with the IPCC report precisely what the zero.
Martin, 42 or 39 or so on is not the mean temperature of the world. Not today. Today is about other 10 or 20 years ago. It was about 15. The mean temperature. 39 is too high. I'm 42.
Oh no! Sorry, it's you mean this year 39?
Yes.
No. This is no. This is not the temperature. This is the temperature deviation here. So we are going about 1 degree higher, and here we go up to 4 degrees at the end of the 20th century higher. It's in this figure. It's just 39 models that were included here.
I see.
I'm sorry for this confusion.
Okay.
Probably I misunderstood your question.
Okay.
Thank you.
Okay. You have answered both questions. Thank you very much. Thank you very
Yeah.
much.
Okay. We
Jörg
have
Martin.
okay.
May
Victor.
I ask you, Jörg Martin? Yes, Victor. I asked you something.
Hello, Victor.
Hello. I would like to know something. You mentioned the biomass burning.
Mm-hmm.
And my question is, if I consider the biomass burning, then we have the production or two effects. One effect is the pollution production, and the second effect is maybe the gas, let us say gas production. Which is more important regarding climatic change in the world? Pollution production or gas production?
Well, there's actually a third factor, and I think this is at the end is the most important. That is the change in the land use, or the change in the biosphere. So by burning large areas, large forest areas, for example, we are removing the possibility of the natural biosphere to take up carbon dioxide from the atmosphere and bind that in the biomass. So I think at the end, this is the most important factor in terms of climate.
Okay.
The pollution itself is not, I don't think it's a big driver for the climate change, although it produces ozone in the troposphere, and ozone is actually a very important, tropospheric ozone is actually a very important greenhouse gas. So it's also a driver of climate change. But I think the land use change is, in terms of climate, the most important one. But of course, it has a lot of adverse effects. I mean, it's deteriorating air quality with health implications and so on. And as we see here in this study,
yes,
this is, of course, to some extent, biomass burning is man-made very directly. People go there and deliberately burn parts of forests or crop bushland or something like that. But the climate change, in particular the regional climate change, and this is a very important factor, for example, in Australia, is related to the ongoing climate change. That is that these circulation changes, for example, as a result of the climate change, drive temperature anomalies here. So it's temperatures that are almost 2 degrees warmer than usual under this particular situation of the polar vortex, stratospheric vortex, and it's much reduced rainfall, and that amplifies the risk, strongly amplifies the risk for these large fires.
Thank you.
Okay, we have Erwin with a question. Erwin?
Yeah, thank you, Ana Cecilia.
Welcome.
Dr. Sinnhuber, thank you very much for this pretty interesting exposition, which is fascinating for me. And just a remark, I'm always looking at the weather reports in Germany, and they tell you the temperature tomorrow will be between 10 and 15, 18 degrees because of different locations. I'm always laughing about here in Chile when they say the temperature was 31.5 and the other was 25.8 or something like that. So it seems that people don't have any idea of uncertainty. And that is where my questions come from. When you speak about 1 or 2 or 3 degrees C, is this a mathematical model? Because I don't know, it's 10 times the temperature in Rio plus 5 times the average in Hamburg divided by the temperature in Karlsruhe, or what the hell is the temperature you use for this? It's really a question because we have uncertainty. And I understood in one talk that it is less uncertain, the difference compared with the absolute temperature. How are these models done? It's strange being graphically so different, in height so different. How do I have an average to compare from 1 year to another, or from 100 years to the next one?
Yes. So what's shown here on the left-hand side are observations that go back 150 years or so. And what's taken, and this is, as you see here, an annual average. in this case, a decadal average in that case, and it's all global average. So essentially area weighted, so you're not taking 100 measurements from Germany and just one from the southern hemisphere, but you need to make sure, of course, that all parts of the Earth surface as good as possible. I mean, of course, there are large areas, ocean areas, and so on, where the observation network is not dense at all, is very sparse. But I mean, there are good temperature measurements for 150 years or so. Therefore, almost all of these reanalyses start at about 1850 that we consider pre-industrial. And there are different ways how to do that. And that's shown here in the different colored curves. And they have some uncertainties that deviate, in particular here in the time of the Second World War, where there are changes and how things were reported, and there are differences, but by and large the differences are small. Here is also, by this shading, is shown the uncertainty that indicates the uncertainty for these decadal averages. And you see they are a bit larger. The uncertainties have been larger in the past than they are right now, of course, because I mean, the networks have improved and so on. But the uncertainty here is, for the global average, is much smaller than the change that we are observing. It's a very different story when we talk about uncertainties for climate model projections, because there are two factors going on. One is we don't know what the future will bring, because we still can change it. I mean, it depends on how we as humanity emit these greenhouse gases. So that, I mean, of course, it can change. So therefore, there are different scenarios where the assumption for the model is that emissions will drop drastically in the near future, or that emissions will continue. And then within this scenario, there's still uncertainty, because not all of the processes are well understood. And this is given here, or indicated a little bit, by this range here. And that can be quite substantial by the end of this century, whether we go at 4 degrees or only 3 degrees or 5 degrees warming, or maybe even larger uncertainty. And one part of this uncertainty, I mean, one part of this is inherent variability in the system. So, I mean, as we know that weather, we can't perfectly predict that, and there is internal variability. But the other part of the uncertainty comes from the fact that there are processes that we not understand well enough. Like, for example, I mentioned these small-scale gravity waves that drives the circulation. And this is one of the motivations that we try to better understand these processes, that ultimately they can be better represented in the model and reduce this uncertainty range here.
If you allow me another question, it's just because of the greenhouse gases that you were measuring around. I understood that one of the latest discoveries is this so-called black carbon, which is a fraction from PM 2.5, which is kind of shielding the radiation. So this is something you are measuring, because for me it's new. You measure NOx, CO2, and whatsoever, but this so-called black carbon is something new. Is that also in your voyages here being measured in an altitude?
No, unfortunately not. I mean, we would like to measure also these aerosols and black carbon and other particulates. Unfortunately, just for practical reasons, we couldn't include that. I mean, we have a payload in the aircraft of something like 10-15 different instruments, but unfortunately these aerosol instruments need different inlets. They have technically, it's also possible to put them under the wings, but just for practical technical reasons, it's not possible to fly that together with our infrared instrument, with the Gloria, because then we would have two things under the aircraft, And that's just for aircraft reasons not possible. So we had to decide whether we go with the Gloria instrument or with the aerosol package, and we decided that we go with the Gloria instrument, which gave us very interesting result. Actually, also on aerosols, by remote sensing, we get some aerosol information, but we do not measure directly black carbon here. But you're right, black carbon is certainly also a very important thing.
And just a last question, you measured or you mentioned gravity waves, and that is for me dazzling. I had no idea that gravity waves will influence our weather. How is that? Because this is supposed to be such a little effect that you have to have 5 kilometers length to measure a gravity wave. How do you think that this is really affecting our weather? It's the first time I hear that. Those completely novel.
First of all, I mean, sometimes there is confusion between gravitational waves and gravity waves. Gravitational waves is something very different. That is, I mean, you know that in the context of black holes and so on. Yeah. So gravity waves are atmospheric waves that are on the scale from a few hundred meters. You sometimes see them if you look into the sky and see sometimes streaky cloud patterns or so. These are small scale gravity waves, and they can have sizes up to 100 kilometers or so. They're called gravity waves because the restoring force for them is the Earth's gravity. I mean, there are other kinds of waves in the atmosphere where, for example, the rotation of the Earth is the restoring mechanism, so conservation of angular momentum. In this case, for the gravity waves, it's similar to ocean waves that go up and down, but here they're internally in the atmosphere. And they transport momentum from the surface or from the region where they are excited up into the atmosphere, where they ultimately break, like ocean waves on a shore break and put momentum and energy to the shore and can cause damage there. In a similar way, these atmospheric waves can break higher up in the atmosphere, deposit their momentum and their energy there, and then drive the large-scale circulation there, and that influences our weather.
Okay. Good.
Okay, anyone else?
Yes. Yes, I have a question.
Okay.
Because I'm working a lot with, or in Patagonia, and right now I'm writing on a paper, and I'm missing one information right now. I didn't do any literature research, but maybe you have a tip for me, like what is the tendency in Patagonia? It's like with the climate change, is it like getting drier and warmer, or is it like, do you have anything already ready, like in terms of regionalized climate change models for Patagonia?
No, unfortunately not. I mean, I don't have the long-term evolution at hand. But of course, I mean, during the campaign and during the preparation of that, we build up nice collaborations with groups in Argentina and Chile. And of course, I could reach out to them and try to answer this question, or bring you in contact with some of these groups if that would be useful for you.
Yeah, it would be nice, yeah. Or if you have some names, or
yeah. Maybe we can come in contact if you send me an email or something like that.
Mm-hmm. Okay, thank you.
I have another question.
Okay.
As you've shown, our lack of understanding of higher atmosphere processes influences our lack of understanding of global climate mechanisms. I'm interested in how large do you estimate is the influence? I mean, are we in a situation where your research will more or less kind of improve existing understanding gradually on climate change, or are we in a situation where we could face entirely unexpected regional impacts of climate change that were not forecasted without your research?
Well, that's very difficult to answer. I don't think this will change our picture of the global climate change significantly. But on the so the global picture is essentially governed by the radiative balance. I mean, we are trapping part of the infrared radiation by the greenhouse gases. That's pretty well understood. The regional changes, for example, things like here, I mean, will the El Niño become more frequent or not? Will the, what is about the warming here of the southern tip of South America and the Antarctic Peninsula? Will that continue or reverse due to the healing of the ozone hole? These things are not very clear in the moment. We don't have too much faith into the climate models in this respect in the moment. And hopefully our research will improve that. I mean, to what extent is difficult to say in the moment, but we know that much of this, I mean, you've seen here, where was it? Was it here? Yeah. I mean, we have different assumptions. I mean, most of the climate models treat the ozone hole like this black curve because they're ignoring natural bromocarbons from the ocean that don't have a trend, but they amplify the human-induced gases because they provide a reaction partner for the anthropogenic gases. And the blue curve is in much better agreement with the observations, obviously. It doesn't make a big difference when the ozone hole closes, but it makes some difference. And this is just one example of the things where we don't have, I mean, we are in some areas, in some detail, we have very large uncertainty, and we can try to improve that. And whether or not that will have a strong or small effect on regional climate change is very difficult to say, because it's essentially like a chaotic system, the weather systems. And I mean, we are, yeah, hopefully we make gradual improvements. Whether or not there will be surprises, it's hard to say. I mean, that's in the nature of a surprise, that it comes as a surprise.
Okay. Thank you.
May I ask another question? Because you mentioned this gravity waves. When you fly, you also measure gravity, isn't it? When you're flying around, you measure gravity, because I know that just beneath South America, there is a very active zone where I don't know what is moving. So if we have in the center of the Earth, we have a mass moving, there is a different gravity. This is in cooperation with trying to find out earthquakes. Chile is very fond of trying to anticipate earthquake, and they have measuring this, because the gravity is changing depending on what this mass is doing, and sometimes, of course, the force is so that our plug is increasing the Andes. Do you measure that also, and is it the same effect then on the atmosphere as we fear about earthquake, that this gravity changes because this strange mass within the Earth is changing, that this will make an effect on the atmosphere? Or
so we are not measuring that directly. No, we are not measuring the not things like, I mean, related to earthquakes. But I know that there are people, I mean, not in our group, but I know that there are people looking at atmospheric gravity waves as a result of earthquakes. And some of them even claim that they are able, by looking at gravity waves, anticipating gravity waves at a very high altitude in the atmosphere, being able to forecast earthquakes. I don't know whether that, well, I mean, if there's a strong earthquake, it may excite waves in the atmosphere that you can measure, yes. Whether you can forecast earthquakes by that, I'm a bit more skeptical.
Okay. Anyone else?
Yes.
No? Yes.
Björn-Martin.
Yes.
Another general question for our information. You are now processing both results from the North track and from the South track. Are there between these two projects so many big difference between the North Hemisphere and the South Hemisphere?
Both. I mean, there are big differences and there are surprising similarities. I mean, just today I've discussed together with my PhD student. She was looking at results from the SouthTRAC campaign here and compared that with a similar campaign we did 5 years ago in the Arctic from northern Sweden, and the results look very similar. I mean, the discrepancies between the climate model simulations and what we have actually measured for the Arctic and below the Antarctic ozone hole look very similar. So that was quite, I mean, it was quite exciting for us because we didn't expect that the mechanisms work. I mean, that it looks so similar. But so that really helps us, because if we find that systematically in both hemispheres we're making the same mistakes in the models, this is of course a much better situation as if we have to treat it that it fits the northern hemisphere but doesn't fit the southern hemisphere anymore. But at the same time there are fundamental differences, of course. I mean, these gravity waves at the southern tip of the Andes, that's really a global hotspot. I mean, because we have these strong westerly winds hitting the high Andes, and we don't have anything like that. I mean, not at that scale in the northern hemisphere. And also the effect of the biomass burning. Where was it here? Or the observations that we had somewhere here. There is biomass burning and pollutants like that in the northern hemisphere, but that seems to be a very regular feature here this is here from the surface to about 12-kilometer altitude. We see huge enhancements here in this PAN and other trace gases. This is really something that we didn't find at all in the northern hemisphere. So this is a very southern hemisphere specialty.
Thank you. Thank you very much.
Last question, Cecilia, please.
Last question.
Last.
Ladies first.
There is another discussion among the scientists, for instance, the geology experts. Some people think that the overall warming of the Earth is a natural evolution, is a new warming era, and the human people, we can make some care to protect us from this warming, but we have nothing to do, because the warming and the temperature is going down with the glacier area and so on, are not under our control. What do you think?
Oh, it's pretty clear. I mean, these strong increases here that we see. I mean, there are natural climate variability, of course, but this strong increase here, without any doubt. I mean, if you look into the IPCC report, hundreds of scientists and publications contributed to that. It's without any doubt this is due to human-made greenhouse gases. I mean, we have a lot of faith in that because we have climate model simulation. I didn't bring a picture like that, but you can look. It's freely available on the internet, the IPCC report. And you can look at, I mean, what would the model show without CO2 increase? Then they are down here. And what do the models show with CO2 increase? They're increasing. Like here, when we don't increase CO2 any further, they stabilize temperature with further CO2 increase. And actually, it looks a little bit as if reality is exceeding the most pessimistic assumptions right now already. So within the atmospheric and climate community of scientists, there's no doubt that what we are seeing here is way beyond any natural variability.
Okay, thank you.
And of course, I mean, if you go back hundreds, thousands of years or million years ago, Earth has been at higher temperatures than today. But Earth will survive. but it will be a very different climate, and it will be very difficult for our civilization to cope with that. It's not that we need to protect the climate, it's we need to protect ourselves and the ecosystems, right?
Okay, Erwin?
Yes, I just had from the picture you showed before. When you were flying, of course, you were measuring the effect of these fires. But as you said, also down here, this South America is a hotspot, and you have the jet streams. How long does it take to homogenize all this shit that we're putting in? For instance, CO2, I understand that it doesn't matter where you are measuring that. You will have the 400 and so on ppm. How fast do we mix these gases so we will have the effect all over the world, as we had many years ago with the atomic trials that they went around the whole world, and now we have distributed this all over. How fast are these movements? How much mixture is between the south and the northern hemisphere? When is this soup completely homogeneous in time frames?
Yes, I mean, it depends on the time scales. We have, as I said, we have observed also, and transport and mixing here is there, that plays a big role. We have observed biomass burning from Australia in South America, or in flights around South America. It takes about 2 days or so for the air to come over from Australia. But of course, it's diluted in between, and we don't find concentrations as in Sydney, for example. And the other way around, we see the highest biomass burning pollutants off the coast of Brazil, close to the source, and it will be diluted further downstream. If you have things that are chemically very long-lived, like CO2, it's not broken down. That's a problem. Therefore, it's accumulating in the atmosphere. It will be almost homogeneously mixed, but there is actually a difference between what you measure currently in the northern hemisphere and in the southern hemisphere, because much more is brought into the atmosphere in the northern hemisphere, and you find more in the northern hemisphere than in the southern hemisphere. So it's not exactly true what you said, that we find the same number all over the world, but it's pretty much mixed, that's true. On the other hand, if we have gases that are chemically short-lived, for example, the PAN, the peroxyacetyl nitrates that are shown from the biomass burning, has a lifetime of a couple of days or so, and then it will be broken down by other reactions and so on. So it will never be totally homogenized. So it depends very much on the time scales. But typically the troposphere is mixed on the time scale of a month or so. Not necessarily between the southern and the northern hemisphere, but within a hemisphere, the mixing takes place on the time scale of a month or so. The stratosphere above is much slower, and we find that things are transported on the time scale of years, actually, not months, because there are not so active weather systems. Everything is stratified. That's the name, stratosphere, and the transport is much slower than it is in the troposphere.
Yeah, my question was because once in a while we are so generous that with our volcanoes we give some ashes to Argentina, and so you have the ashes going down in Buenos Aires, which are being on the plume as you show there. So that is pretty high. But then once in a while this is homogenized all over, and of course ashes do not disappear. They precipitate like.
They precipitate, yes.
Yeah. So it happens that it all flies around. But we get it back from the other side. So via Australia, we get some ashes back, right?
Ultimately, yes. I mean, if the ash is not subsiding down and precipitating out in the meantime, yes.
Yeah. Okay. Thank you.
Okay, I think that is all for today. Okay.
Yes.
Next Friday we start the meeting at 12:30. Cecilia is asking for that here in Argentina, and we are going to send you a mail with all the information. Don't worry about that. Okay.
Thank you. Thank you.
Okay.
Fine.
Thank you. very much, Björn, for your time.
Oh, thank you.
And your
Thank you.
presentation. And okay, see you next week.
Okay.
Thank you
Was
very much.
nice to be in Argentina
Thank
and
you.
Chile for a short time. Thank you.
Bye-bye, everybody.
Bye-bye.
Bye.
Bye-bye.
Okay.
Adiós.